Welcome back, everybody. After a day of recording all of this without audio, let me try over. What I have for you today is an experiment of how we think about rewriting something like a software package. I claim that really at the heart of this is rearranging our logic. It's how we think about a problem that's a way of rearranging the steps in a way that doesn't change the actual implication, but might terribly change how we actually work on it. One of the things that we need to get used to is understanding the pieces of an argument as little components that can be moved around like Lego bricks. So let's take a look at an example of one of these tasks. I have in front of us a simple task. We're trying to design a piece of software to run our printer. Our printer has a few things that control it. For example, it will only print if there's paper in the printer. It will also only print if there's a print job in the print queue. These are the situations that we would understand as kind of minimal assumptions, but take this as a hint at a much more complicated view of your printing system. So what's the task that we should design for? We should design for the fact that if the printer has paper and the queue is not empty, then the printer should be printing. We don't want printers to be sitting there idle when there's a job to do and they're able to do it. So that's the goal of our printing program. However, there might be reasons to separate these concerns. For example, perhaps checking constantly on the printer, having enough paper, is a delay. We're waiting for the network to connect to the printer, asking it to take time away from printing to count whether it's got paper and come back to us. Whether that's realistic or not doesn't matter. I'm just trying to separate our logic so we can see the process of reorganizing our program. So let's take a different sentence and see if it's considerably the same. If there is paper, then if the queue is not empty, the printer will be printing. Are these the same statements? Are they related? Does this one imply this one, or does this one imply that one? Are we allowed to rewrite our program with the second task rather than the first task? This is the logic we want to explore, and sequent calculus is perfectly placed to describe this. In fact, I've already put some sequent calculus on the board in disguise. You'll notice I've separated a premise from a conclusion. What I'm trying to see is if my conclusion would follow from this premise. Is it enough to satisfy this? Would I necessarily have to do this? This is a premise conclusion setup, but it's actually more than that. Inside of this premise, we see there are further premises and conclusions, just like on the denominator. This premise conclusion factorization is what sequent calculus is good at. Now, it works better to visualize this by trying to draw pictures and put names and labels to things, so let's try to do that. Let's isolate the ingredients we have. At the moment, we have at the top here, we see an if and a then. We know that if then is one of these implication symbols. We replace that with an arrow. Now that arrow has two pieces to it. One is the hypothesis, the values that go before the things that will entail the results, the conclusions. So the conclusions occur right here. The printer will be printing. Let's give that a name. We can think of that as one isolated task, that the printer is printing. It's a state of being in our calculations. Let's call that C, the conclusion. We want to end with that conclusion. Notice this same sentence occurs in our conclusion for this total story. We also want to end with a C somewhere. Only now we realize that the if-then is ending from a different premise. If we look at the premise for this conclusion, it's all of this here. It's the there is paper and the queue is not empty. So let's call that thing H. This is the hypothesis that we have in the top. So we've now collapsed the entire premise on the top to one implication. H implies C. This brevity gives our brain a time to think about what's happening. The manipulations that might be occurring will look simpler when they're small. However, it's also okay for you to write short little words here. You could write hypo and conclude or something like that, or hypothesis and conclusion. You don't need to abbreviate it all the way to one letter. What else is going on in the denominator? Here we see there's a genuine change. We notice that no longer are we taking the entire hypothesis. In fact, we've broken it apart into two separate hypotheses. There is paper occurred here, and the queue is not empty occurred there. What allowed us to break them apart is that we realized that up here in the hypothesis in the premise, there was already a compound statement. And that was because we had this particular operator in the middle. And by putting and in the middle, we created this larger H. But we can now see that if we named these parts, we could break it apart a little bit. So I'll name this part here A, which reoccurs here, and I'll name this part B, which reoccurs there. So we now see that the top and the bottom are arranging the A, B's, and C's in possibly different ways. In the top part, how we got A and B together was with the linkage and, we would call it conjunction. So we had A and B replacing the H. Together, they gave us A and B implies C. Now what's happening on the bottom? On the bottom, we recognize there's another implication. This outside if then is also an arrow. So there should be two arrows in what we're doing here. Our first arrow starts with A. So we have A implying something. What does it imply? All of that, which starts with B and implies C. If we see these together, we start to understand what the real difference is. Up here, we have an A and B implying C. Down below, we have A implying B implying C. Now this gives us an opportunity for our sequent calculus. Instead of having to reason about whether the logic of the two sentences are the same using natural language, we've reduced it to whether the symbols manipulated in some way could go from the top to the bottom. And that's a standalone question. We could, in now, look this up or compute ourselves. We could go to Stack Exchange and ask some experts for ideas. The key thing about breaking it down into a sequent calculus is that it gives us a brief explanation that has nothing to do with whatever secret mission our code is about or all the minutiae that might be distracting. We've made a very specific claim about logic, and indeed this is true or it's not. If we find it's true, we continue on our way and program it however we like. If it's false, we might modify it and see if we can get a better version of what we're trying to do. So what we'll do next is we'll start to explore how to use the sequent calculus as a method of calculation. We'll think of these as operations, similar to plus and times, including the arrow as another type of operation. If we can see how to manipulate the operations, maybe we can rewrite this, like writing a polynomial as a factored polynomial. It may look different, but have the same logical content. That's where the sequent becomes a calculus. The sequence are the pieces of little sequences, and the calculus is the way of calculating with it. And that's what we'll develop next.